I hope to wrap up this chapter today, chapter 3, which means, now that you've already had your mechanics test, you can get ready for E&M. So what we were doing was multipole expansion. And you have an extended object, and you locate any point in the object by a vector r prime, and you're interested in computing the potential at r. This is what you're interested in. Of course, the potential depends on the separation angle. This angle between r and r prime is what we call alpha. Okay? So obviously, alpha depends on r and r prime. So from a simple notion of kq over r, for extended objects, we can extend this to rho of r prime d tau prime over. Okay, that's where this is effectively coming from. But we have done a better job of, so this is now recall. Well, all of it is, but 1 over r is equal to 1 over r times 1 over square root of 1 plus epsilon. I would like for you to look up to make sure I am correct. This is r prime over r prime over r. What is it? Minus 2?
2r prime over r.
2 cosine alpha. And when you hear the term expansion, you know it is a Taylor expansion. And this is obviously the guy that's being expanded, and you can see why we call it epsilon, because if r is much greater than r prime, this becomes a very small number. In real life, r prime is just microscopic distance, and r is a very large distance. Okay, so this is truly a small number. And the Taylor expansion, I don't recall the exact, I think the first two is that. You can verify. I have written this last time in class, but one more time. 3 over 8 epsilon squared minus 5 over 16 epsilon cubed. Next one is going to be plus, and so on and so forth. It's an infinite series. So what we're going to do is every time we see epsilon, we're going to plug this in on the right-hand side. So I would have V equals K rho r prime over r. Now comes 1 minus epsilon over 2, r prime over 2r, r prime over r minus 2 cosine alpha. What's the next one? Plus 3 over 8 r prime, I don't even know why I'm doing this, just to show you where these terms come from. 2 cosine alpha squared, because very soon I'm going to get tired, and of course we have to integrate all of this. recall, not that it's important for us, d tau is what? R prime squared sine theta prime, dr prime, d theta prime, d phi prime. Correct? Yeah. So, to desired accuracy, you can do this integral. This is already r prime squared over r squared. But there's if you're going to keep it up to r prime squared over r squared, you have to be careful. There's an r prime squared over r squared coming from this term. Yeah? So you have to do a little bit of algebra and simplification. You can test this out on your own, but it's just algebra. I recommend that you do. What you're going to end up doing once you simplify and you collect factors of 1 over r, what you'll find is the first term is 1, no surprise there, plus r prime over r cosine alpha plus r prime over r squared. I'm just going to write it one more time so that we don't need this integral anymore. Does this look nice to you? Really? I haven't. Let me explain. 1. Whoa. Why did this come about at all? Crazy, right? This has nothing to do, seemingly, with Laplace's equation and separation of variables, or does it? It's the Halloween special. So, look, I can write this in a nice way. There's this extra factor of r. And this is very often written in this final form. We are, at the end of the day, teaching physics. So I'll factor out the r's because these terms do not get integrated. But this is r to the n. There's an extra r over here. So 1 over r to the n plus 1. Now comes the integral. Rho r prime to the n pn cosine alpha d tau prime. And this is the expression for potential. So if you have a bulk distribution of charge, it is not possible for you to exactly integrate. Well, you can. If you really wanted it, you could write a code for it, right? And you can just do it very quickly. But you can also use this expansion. But this expansion might have meaning, a little bit of intuitive things. And then we can know what we want to hang on to, what we don't want to hang on to. Typically, in the undergraduate course, which this is, we hang on to the first two terms. We give it names. If you're in graduate school, you hang on to the third term. If you are doing research, maybe you'll need the fourth term of accuracy. Very seldom. Very seldom. The first term, n equals 0 term, I'll write this down in detail, is called the monopole term. It is determined by the net charge, and net charge alone. The second term is called the dipole term. The third term is called the quadrupole term, and so on and so forth. It is called the quadrupole term. Even moment of inertia works out that way. Right? So let's look at the n equals 0 term. This is called the monopole. So that's equal to k over r, because n is 0. Rho r prime. Well, that is just pretty neat. The dominant term is as if it is a spherical distribution. Yeah? So this is why for physicists, everything is a sphere. You may have watched Big Bang Theory where they talk about calculating something where penny can tip over a cow or something like that. So Sheldon does his calculation, assuming that it's a spherical cow, meaning he hung on to the monopole term. Well, it's going to be smaller, as we'll see. Yeah? So if you have a big blob far enough away, it's a big blob, it's a sphere. You don't see the antenna on the Death Star. Yeah? Well, but you want to do a little better. So, well, let me... As I'm finishing up the chapter, we don't have a whole lot to do. So are we on board? We have some time. We can breathe a little today.
What happened to that, the second r prime to the power of n term again?
Yep, it's to the 0.
Oh.
P0 is 1. Good, good. N equals 0.
The other one was 1.
What's that?
I knew the other one was 1.
Yeah.
And then for some reason I was thinking n was 1.
Yeah, right, yeah.
It was weird.
I do stuff like that. N equals 1 term. And we'll see why this is called the dipole term. Remember, we studied the dipole, correct? And so that's going to come back. So that is k over r squared. See, n equals 1. This gives r squared. So watch it, Ashik. Here, rho of r prime cosine alpha d tau. P1 is just cosine.
Prime. D tau prime.
D tau prime, correct. And I'm glad I didn't remove this picture. So from this picture, what is r hat dot r prime? It's the magnitude of r hat, which is 1, times magnitude of r prime, well, which is what we call r prime, times cosine of the angle between them. So guess what? That's exactly that. Therefore, I get I'm going to replace this with this. Except I'm not integrating over this sucker, right? I'm only integrating over that. So I'm going to write it as r hat dot correct? Look at this. This depends, like all moments, this depends only on the internal geometry. It has no R dependence over here. So that is a good thing that we can name. Define the dipole moment of the charge distribution by the vector P, where P is exactly what I told you, rho of r prime. What makes the right-hand side a vector? R prime. Good, 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 good. Yeah, James? Good?
Get rid of that vector because we know it when we go into potential.
Yeah, potential becomes a scalar. So then I get the final nice expression. Then, if you want to calculate the next level, so typically you would hang on to the monopole term. You don't get rid of it, but you just call it the monopole term, and then you hang on to the dipole term as well. K P dot r hat over r squared. So let's see. So if you have the potential falling off as 1 over r squared, that's a telltale sign that there is a dipole moment to it. And whatever the dipole moment is, it's this guy. Now we have seen a simple, or perhaps even an ideal dipole. So of what we have seen. One of the things that I would love to do, but I won't, or maybe I won't, is give you a funny shape and give you a charge distribution, and I say compute the dipole moment. Well, can you do it? Well, question is, can you integrate? If I'm going to give it to you, I'm going to give you a simple geometry, a spherical cow. And I'll make sure that it's integrable. Yeah? Huh. All right. So, we've seen this before. Minus Q. This is d over 2, and this is d over 2. How can I compute the so, by the way, Martin or anyone else who's studied chemistry, if you need to know the dipole moment of the water molecule, you'll use either this formula, where charges are delta function charges. So now you can locate the hydrogen and oxygen molecule by some delta function and integrate it out. But when you do that, you'll get a simple formula that you get from here. In this case, there's no integration to be done. There are two charges, right? So I can just do it as Q plus R plus Q minus R minus. So it's going to be Q d over 2 z hat. See? Charge times the vector distance. And then for the same thing for the next one, minus Q, because it's minus Q, minus d over 2 z hat. That's where they're located. And therefore, what is it? Q d z hat. I can even write this as Q d. That's the dipole. This is the physical dipole. And when you put this back in here, you will get exactly the same answer as you got before. Now, is everyone clear how I got that? Nothing makes me happier than taking a simple problem and doing it the long way. So let me clarify that, because we have the answer already. I don't want to do that. Do I? That's true. Gotta make your life slightly. R prime minus d over 2 z hat. You would think it ends here. That looks right, correct? The two charges? Yeah, but it's not quite right because the way delta function is defined. I'll show it to you. Or I can use, would you be happy if I use spherical coordinate system? I mean, sorry, Cartesian coordinate system? Then I don't need this. You know why I need this? Because that integral has that r squared sine theta d. I'm going to do this in Cartesian coordinate system. And then you'll be perfectly happy. All right? And I'll just do this integral. When I do the integral, I would get Q dx is at 0, dy is at 0, d c prime minus d over 2 c prime hat. Oops, c prime. I don't think that matters. C prime is exactly that. vector. Then I have the location, which is what? What is the location? Z prime, Z hat, dx, dy, dz. Dx and dy gives you 1. You put x equals 0, there's no x. Y equals 0, there's no y. And then I get q. What happens to this integral? So I have z prime minus d over 2, z prime, z hat, dz prime, dx prime, dy prime, dz prime. What does that mean? All I have to do is replace z prime with d over 2. Correct? So then I would get what? Q times d over 2 z hat. And similarly, I can compute the next one. You see that? The x coordinate of the charge is 0, y coordinate of the charge is 0, z coordinate of the charge is located at? Yeah. And this is the vector x prime x hat, y prime y hat, z prime z hat. But x prime y prime would give me 0 because of this. So only the z integral would survive. And that using the delta function. So yeah, remember r prime is x prime x hat plus y prime y hat plus z prime z hat. But when I do this integral, I'm going to get 0 because of this delta function. Replace x prime by 0. Replace y prime by 0. But replacing z prime by d over 2. And that's how I get this term. And the other way, you'll get the other term. So again, we know this. It is possible using delta functions to simply calculate potential like we did before. Did I make it worse? As I said I would? Yeah, you can ignore that part. You know, sometimes intuition is better, but you should be able to carry it through. I realize I've skipped steps, but that is a good thing to do on a Friday because I know you're begging for some action on Saturday and Sunday. So you can clean that up. Okay. So, the electric field due to a dipole, not just any dipole, we'll pick our dipole. We don't care about the details. We'll just pick our dipole to be just a fixed vector we'll just call P. It is centered okay. The dipole itself has some magnitude constant magnitude P in the direction z hat. So then the dipole potential is K over R squared. And if I need the electric field at any point, or the potential at any point, I get P dot R hat, oh, not R squared. And because I have picked my P along the Z-axis, the angle is indeed theta. So I have cosine theta over R squared. So when I say electric field, what do I need to find? Very good. Negative gradient. The gradient will have three components: the R component, theta component, and phi component. The geometry looks very axisymmetric, so I don't expect a phi component of the electric field. Look up the formula for the radial component of the gradient in spherical coordinate system, and what do you get? I think it's just partial with respect to R.
And then the next one's 1 over R partial with respect to theta.
So this, is it just this? For the radial component? I'm just writing the radial
Yeah.
component.
Yeah.
Okay, so that's negative Kp cosine theta. What's the derivative of 1 over R squared? Is it 2 over R cubed? R to the minus 2, so minus 2 R to the minus 3, right? Okay. And E theta is, what did you say it was?
1 over R and then partial.
1 over R dv d theta. So that is minus Kp over R cubed. Derivative of cosine is what? Negative sine theta. You can verify at home. Well, there's a partial with respect to phi. There's no phi. There's nothing to verify. I can write this vectorially. Huh, did I make a mistake?
I love you guys.
Huh.
Is that over R cubed or?
E theta?
Oh,
There's a 1 over R there. Yeah, yeah. And if you graph this out, the textbook has a good picture. If you graphed and let's superimpose the dipole. That's the dipole itself. If you plot this function out, this vector field out, the electric field lines simply do this. It's a perfect dipole field. And over here it'll go that way. It might be a bigger loop, but then it comes back around because the net charge is 0 for a dipole. Yes.
What do you mean when you say because the net charge is 0 for dipole? Everything?
Well, there's no monopole term for a perfect dipole. So a dipole, no matter what it is, you should visualize it as an effective positive charge separated by an equal amount of negative charge. So, it's a smart answer, but it's the truth. Monopole terms fall off as 1 over r. Dipole terms, potential-wise, fall off as 1 over r cubed. So by definition, this is a 1 over r cubed guy. There's no 1 over r. And that's why every loop eventually comes back around. Because remember, the field lines emanate from, you know. But on the other hand, if you only had one charge in the universe, then you would have just field lines emanating, and it doesn't impinge on anything. These are open field lines. These are closed field lines. Yeah? So if you want a nice looking graph like this, and if you wanted to plot it, this is the vector field you would plot. But its strength falls off as 1 over r cubed. So one way to maybe even make that clear is when I go far away, this line sort of fades out, right? And then comes back and becomes strong. Because it's not equally strong along the loop, it just drops off. I'm done. So we'll begin with chapter 4.